All right, folks, thanks for coming back. What we're going to talk about now is ways that we can turn the carboxylic acid into an acid chloride. That's sort of the first one as we go down that list that was on the right-hand side of our acid derivative table. If you need to, go ahead and write that down on a separate piece of paper or keep it handy because I can't reproduce it every time we go to a new slide. And that's actually pretty important stuff. The principal way this reaction is carried out is using an old friend of ours, thionyl chloride with trace pyridine. Now, you've seen thionyl chloride before. Where, pray tell, was that? Well, you've seen thionyl chloride before. I'm going to kind of tuck it up in this corner as a way of turning an alcohol into an alkyl chloride. And we're doing roughly the same things here. The mechanism is slightly different, but when we're done with this, I want to talk about the energetics of it so we can really get a good feel for what plays a role in how these work. So to start with, for the mechanism, what I want you to do is look at this. Here's our carboxylic acid. There's the acid chloride. The carbonyl oxygen nucleophilically attacks the sulfur and then kicks off the sulfur-chlorine bond. I forgot to tell you one thing here. It all happens at the same time that this oxygen forms a pi bond between here and there. So your intermediate looks like this. Sorry, pen freaked out on me for a second. Sorry, folks, the tech gremlins are upon me today for some reason. So you wind up there. With this as your intermediate. The chloride anion you just kicked off is going to nucleophilically attack that carbon and then give you this intermediate. I'm going to go ahead and erase that so I have a little bit more room to play with. So you get this. Now, I'll be very honest with you, I have no idea what that structure is called. But here's what happens next. Reform the oxygen-carbon pi bond, break off the oxygen-sulfur bond, and then kick off that last chloride. So what you make is this. Plus SO2 plus Cl minus. And all we have to do now is remove that proton. Now, there are several ways you can do it. The pyridine would probably do it. The chlorine could too, but it would disassociate right away again. And there's what you make. You make your acid chloride plus SO2, which is a gas, plus hydrogen chloride in one form or another. Okay, let's go look at the energetics of this for just a second, because something kind of cool just happened. If you go back and look at that acid derivative table I gave you, what you'll notice is the carboxylic acid and the acid chloride are quite different in energy. In fact, the overall process for this is endothermic. Also, as just a brief reminder, the energy of activation for forward is greater than the energy of activation reversed. This shouldn't be. Endothermic reactions aren't particularly well favored. Well, they're not. But what makes this go is the same thing that made turning the alcohol into the the alcohol into the alkyl chloride go, which is one of your components, sulfur dioxide, leaves as a gas. So in that reaction mixture, the sulfur dioxide leaves as a gas, meaning you cannot reverse. You cannot make this go backwards. So this is our way of tricking Mother Nature into letting us do a fairly strong endothermic reaction. Okay, so now, with that in mind, let's go ahead and look at the next reaction that we're going to do. Oh, pause. Sorry, folks. Like I said, the tech gremlins are on me today. So this is going to be it for this one. I'll put a few more up later today and tomorrow. What we're going to talk about after making the acid chloride here is we are going to talk about all the other things we can do with it, which is making all of those derivatives underneath it. All right? So for now, hope you're doing well. Stay safe, and I'll write more to you soon.